In the next set of videos, we're going to look at a numerical integration. So why would we ever want to use numerical integration? So a couple of examples. If we have a large building which sticks up right into the Earth's atmospheric boundary layer, we're going to have very large wind forces, and these wind forces are going to depend on the velocity of the wind, and that changes with elevation. So in order to determine the wind force, we're going to need to estimate what the velocity is at different heights and integrate that over the faces of the building. Another example is looking at solar power. So solar power provides electricity by means of heat engines or maybe photovoltaics, and the total amount of heat energy that you can extract in any given system can be integrated by integrating the heat flux during the daylight hours, and that may change as a function of solar position and depending on exactly the shape of the panels and where they are. So integration is actually a very important thing in the real world. There are two main types of difficult integration problems, in other words, places where we would want to do things numerically. The first is when we only have discrete values of a function, for example, experimental data, or perhaps that example of the heat flux on the building. We may have measurement points and they will give us data points. We don't have a function that tells us what our heat flux is equal to in different parts of the building. So we only have measurements, and we need to use these to integrate over the entire surface, or at least make an estimate of that integral. The other place where we need to do numerical integration is when the function is very complex. For example, the function that's written here, I defy anyone here to calculate an analytic integral for this. In fact, even go away and use Wolfram alpha, I'm sure you'd have some problems. So in both these kinds of cases, we need numerical integration, and that's what I'm going to be talking about in this unit when I use the word integration. All numerical integration formula are based on adding up the integrand, that is, the function values, at a sequence of points. And the general goal is to obtain the best accuracy with the least number of a function evaluations. So sometimes, in some cases, the function evaluations can be expensive. We need to make a distinction, and I'll do this right up front, between open integration formula and closed integration formula. A closed formula is a formula that includes the data points at the start and end of the interval. So if we're trying to integrate this function as seen in the figure at the bottom left, we include the function values at these points here in order to estimate the integral between a and b. An open formula, on the other hand, has integration limits that extend beyond the range of the data. So for example, we have data points here and here and here, but we want to calculate the integral from a to b, but we don't know what the function values are at a and b. We can do this using what are known as open formula. Often these are used in the solution of ODEs and in other special cases that we'll have a look at. So we're going to be looking in the next small set of videos about integration for equally spaced data points. And there's a family of integration approximation that are known as the NewtonCotes formula. And the NewtonCotes formula we did in Eng 1060, so I'm not going to spend a lot of time reviewing them here. You are more or less expected to know this already. The basic idea for all of the NewtonCotes formula is to find, or calculate, a set of function values. So for example, if we have a set of x values x1 through x4, we need to somehow know what the function values at these 4 points are. Once we have those function values, the idea is to fit a polynomial of some degree to the data values. So we fit an interpolating polynomial that passes exactly through the data. Then we integrate the polynomial exactly. So if our polynomial is approximately equal to f of x, and we'd like to think it is, then the integral that we calculate is the integral of our polynomial is equal to the integral we are trying to calculate is the integral of f of x, and that's approximately equal to the integral of our polynomial, but there will also be an error term. And the way in which this error term changes as we change the spacing of our points is very important. Okay, also important is the degree of the polynomial is going to determine the accuracy of our integration.